Okay, everyone. Well, thank you very much. I apologize for the technical difficulties we've had. I'm very excited to welcome you here today for the Paleosalinity Proxy Primer through SGP, which is basically our attempt to provide an accessible forum for people to learn about a number of different geochemical processes. All right, well, I'll just continue on with these brief intro slides, and then we can try to screen share again. For many of you on this call be familiar with SGP. For those of you who aren't, this is an open sedimentary geochemical community that's aiming to aggregate and analyze geochemical data across Earth history. You can check out our informational website and search website here. We have a number of samples and results in our database in our phase 2 release that's been built by more than 200 researchers worldwide. One thing that I'm excited to announce is that if you go to the SGP search website, you'll see this little note, which is that we currently have our SGP phase 2 data up in soft release. We are still making a couple of little changes there, but you will be able to access basically 99% of the phase 2 data release. If you do need to still access the phase 1 release, it can be found at that little link. Just looking ahead to our 2025 schedule, we have a number of exciting events. Our first Proxy Primer today, and then looking ahead on May 14th, we have one from Dr. Anne-Sophie Aim on calcium magnesium isotopes. We'll be having an in-person meeting at GSA where there'll be a couple of quick updates as well as a social hour. And then at some point in November or December, we'll be hearing from Dr. Jessica Whiteside on biomarkers. So with that, so Dr. Algeo did his undergraduate and master's degree at Georgia before going on to his PhD at Michigan. He's now a professor at the University of Cincinnati with appointments at Chengdu and Wuhan in China. He has received a number of awards and editorships that are too numerous to mention here. Although I would note that many of us grew up reading his foundational papers in shale geochemistry and also benefiting from his detailed and very useful comments, both as editor and reviewer. He's received a number of exceptional reviewer awards, and many of us have experienced his dedicated work as editor.
So I'd like to thank Eric kindly for his invitation to speak to you today. My topic is going to be elemental salinity proxies. Go ahead and advance, please. So salinity is one of many water mass properties that paleoceanographers seek to reconstruct. There's a list here in the upper right, and there are a variety of different kinds of proxies that can be used in order to try and determine these features in paleo water bodies. And of course, elemental concentrations is one tool out of many. There are also stable and radiogenic isotopes, biomarkers, biotic and mineral and rock components. Salinity is one of the most fundamental properties of water masses, though, and one that we have a deep interest in reconstructing in deep time systems. Go ahead and advance, please. So in continental areas, one may encounter mainly freshwater systems. In the open ocean, it may be something very close to marine. But in coastal regions and restricted basins, there's often a lot of salinity variation, and that's what's illustrated here conceptually. We see both vertical and lateral salinity gradients associated with restricted basins and estuaries and saline lakes. And all of this represents salinity variation that we're interested in reconstructing. Next slide. So there are several types of salinity scales that are out there. I like this one here on the left because it's very straightforward and the terms are easily understood. Freshwater means very low salinity, typically less than 1 part per thousand, or PSU, which stands for practical salinity unit. Marine salinities are in the range of about 32 to 38 parts per thousand, and brackish falls in between. Now, it's very useful to distinguish low from high brackish conditions for reasons that I'll show you in another slide. Above marine, of course, we have hypersalinity, hypersaline conditions. Salinity shows strong variation. The density shows strong variation as a function of salinity variation. The two are strongly correlated. Temperature, of course, plays a role there in controlling density variation, but salinity is often a dominant determinant of density variation. And density is important because it determines water column stratification and water mass circulation patterns. Next slide. An example of the role of salinity in determining density, the water mass density structure, is shown in this slide here. You're looking at variation in density in sigma T units plotted across the diagram by the blue lines. And that's a function of both salinity, which is shown on the x-axis scale, and temperature, which is shown on the y-axis scale. This is for the open ocean. It shows that there are separate trends for the Pacific, Indian, and Atlantic Oceans. It does show that salinity is important, although the range of salinity variation seen in modern ocean systems is limited. Next slide. One sees a good deal more salinity variation in estuarine systems, so the lower parts of rivers where they come into contact with the ocean. The slides here show several examples of this. The two slides on the left show variation in the carbon isotopic composition of POC, or particulate organic carbon, in two different estuaries, one in the Netherlands, one in Kenya. You can see the relationships are different, but in both cases, there's a strong relationship between salinity and the carbon isotopic compositions. And this pertains to many other water mass properties as well. So in systems where there's salinity variation, salinity is often a dominant determinant of variation in other water mass properties. The slide in the upper right here shows salinity variation on an annual basis in the Guadalquivir estuary of Spain. It's plotted as distance from the coastline, so 0 is the mouth of the river and 40 is 40 kilometers upstream. Of course, at the mouth of the river, one sees salinities close to marine. Upstream, one sees freshwater conditions. But in between, there's considerable salinity variation. And that variation is pronounced at the scale of an annual cycle. And that's what's shown by the red arrow. So at a distance of 10 kilometers upstream, salinity varies from about 10 PSU to 35 PSU annually as a function of the amount of runoff and flow through the Guadalquivir estuary. So salinity variation is pronounced in these kinds of coastal systems. Next slide. So I mentioned a minute ago that it's important to distinguish between low brackish and high brackish conditions. The reason for that is that it's strongly related to the nature of the biota that is present in estuarine systems. So the diagram here is a form of the Raman diagram, a well-known diagram showing diversity of different assemblages as a function of salinity, which is plotted on the x-axis here. And the biota are grouped into three categories: those that are found in freshwater environments, shown in green on the left; those which are found in marine environments, shown in purple through most of the diagram; and then those that represent estuarine species, which are shown in blue in between the other two. You'll notice that diversity is lower in these brackish settings because, in particular, the fluctuation in salinity often limits what species can successfully occupy such habitats. And moreover, one of the important points here is that marine assemblages are seen under high brackish conditions, that is, where salinities exceed roughly 15 parts per thousand. The biotic assemblage is often still dominated by marine species. But when one gets below about 15 parts per thousand, the nature of the biotic assemblage changes to one more characteristic of estuarine conditions. So that distinction is useful and can be correlated with biotic assemblages. Next slide. So I'm going to briefly talk about salinity variation in three modern cratonic seas. The reason is that these are some of our best analogs for ancient cratonic seas, and much of our stratigraphic record, not coming from the deep ocean, comes from such environments. So it's important to understand the nature of hydrographic conditions and these kinds of epicratonic marine systems. I'm going to talk briefly about Hudson Bay in Canada, the Baltic Sea in Northern Europe, and the Gulf of Carpentaria in Northern Australia. Next slide. These diagrams relate to the Baltic Sea. And the upper one shows variation in density. The units are sigma T units, but salinity variation would follow the same pattern. And what one sees is the lowest values in the inner parts of the marine system. So the northern part of the Baltic Sea, where salinity is scarcely above fresh water. And then increasing salinity as one moves in the oceanward direction and also to deeper environments in the central Baltic. So there are very pronounced lateral and vertical salinity gradients in the system. And ultimately, those gradients control the density of the water mass and the redox conditions seen within this basin. Redox conditions are shown in the lower graphs. The area of intense anoxia in the Gotland Basin and selected other basins is shown in the lower left. And then the history of redox variation in the Gotland Basin over the last 50 years is shown in the middle lower diagram. And there's fluctuations back and forth between oxic and anoxic conditions that are a function of overspill of water masses from the Kattegat into the Baltic. That's shown by the dashed arrows in the upper diagram. All of this ultimately is controlled by salinity variation. Next slide. And these two diagrams show cross-sections of density variation in Hudson Bay at the top and in the Gulf of Carpentaria below. It's worthwhile to contrast these two because they're found in different climate belts. The upper one, Hudson Bay, is in an area of humid conditions and hence positive water balance. So there is significant freshwater runoff into Hudson Bay that produces a low salinity surface layer, significant vertical salinity variation, and water column stratification. In contrast, the Gulf of Carpentaria is found in an arid climate zone, so it's characterized by negative water balance. In other words, evaporation exceeds precipitation and runoff into the basin, as a consequence of which there is no low salinity surface layer. And in fact, salinity increases into the interior part of the basin because of excess evaporation there. And the salinity, the isohaline lines are vertical in this diagram rather than being horizontal as in the upper diagram. So it's a completely different pattern of salinity variation. And in the Gulf of Carpentaria, there's no water column stratification. Next slide. Now, there are a wide range of proxies that can be used to evaluate salinity conditions in ancient geological formations. Some of these depend upon biotic assemblages. Some depend upon the presence of evaporite minerals, which are an indication of hypersalinity. Some other, a range of geochemical proxies can be used. Various elemental ratios, isotopic ratios can be used potentially to reconstruct salinity in ancient formations. However, all of these require analysis of some specific component. They're not based on bulk sediment analysis, and they have limited applicability. For example, if they depend upon the presence of a specific fossil taxon, obviously that taxon must be present before the proxy can be applied to salinity analysis. So there are significant constraints on the utility of all of the various proxies shown here. Next slide. Here's an example of a geochemical proxy based on elemental content of the planktic foram Trilobatus sacculifer. Salinity on the x-axis is plotted against sodium-calcium ratios on the y-axis. You can see a nice correlation in the left-hand diagram, suggesting that salinity can be reconstructed down to a few parts per thousand based on the sodium-calcium ratio of this particular foram where it is present. However, this is a taxon-specific relationship as seen in the right-hand diagram, and other taxa show different relationships of sodium-calcium ratios to salinity, meaning that such proxies have to be calibrated on a taxon-specific basis, and that too limits their utility. Next slide. So a few years ago, I became interested in the question of whether there were any elemental proxies that could be applied to bulk sediment samples to evaluate salinity conditions in the depositional environment. And a PhD student and I worked on this issue, and we examined a lot of different potential proxies and concluded that these three yielded the best results for evaluating salinity in ancient shale formations. And this initial work was confined to shale formations. The three proxies are the boron-gallium ratio, the strontium-barium ratio, and the sulfur-TOC ratio. The reason for the choice here of normalizers, for example, normalizing boron to gallium, is because those two elements belong to the same group. They show the same valence, and they show similar concentrations in average crustal shales. The same applies to strontium and barium. They belong to the same elemental group, have the same valence, and show similar concentrations. So it, I think, is best to normalize two elements that show the same general patterns like this. Sulfur TOC is a little more complicated because the amount of reduced sulfur that winds up in a formation depends upon the presence of organic carbon and paired redox reactions between the organic matter and what is initially sulfate in the water that's converted to reduced sulfur, hydrogen sulfide, and then fixed by reduced iron. So that requires the presence of both organic matter and reduced iron in order to preserve sulfur and therefore make the sulfur TOC proxy a viable proxy for salinity determinations. And that creates some limitations on its use. In fact, I will note in passing here that based now on about 7 years of research, it appears that boron-gallium proxy is the most robust, the most reliable. The strontium-barium proxy works in some settings, but it's also subject to a number of caveats. In particular, anytime there is carbonate present, there can be excess strontium sourced from the carbonate that will confound the salinity signal and make strontium-barium unviable for paleosalinity determinations. And so more and more, as we move forward with this work, we've been focusing our work on boron-gallium and a related proxy called excess boron that we can apply to carbonate facies in order to evaluate paleosalinity. There are very distinct advantages to having elemental salinity proxies that can be applied to bulk samples. Shale is the most abundant type of sedimentary rock, and so that was the reason why we focused on salinity proxies for it first. Being able to analyze bulk sample means that there's no need to isolate specific fractions of the sample, and the proxy is going to be applicable over a wide range of facies and salinity conditions. Okay, next slide. So a key study was the one that I published with this PhD student, Wei Wei, who came from the China University of Geosciences in Wuhan and worked with me for a couple of years in Cincinnati. We published this paper in Geochimica and Cosmochimica Acta in 2020, and this is kind of the foundational study for all of the subsequent work that we've done on elemental salinity proxies. Next slide. So what the important points to note with regard to these proxies are, number one, the concentration of boron, strontium, and sulfate in water masses. And here I'm referring to marine water masses and fluvial water masses that are in direct contact with the ocean, and then the estuarine environments in between. In those systems, the concentrations of boron, strontium, and sulfate correlate linearly with salinity. And uptake of those particular ionic species by the sediment mean that it's possible to record the salinity signal in a given depositional environment. For boron and strontium, the process is the same. These ionic species are taken up in direct proportion to their concentration in the water column by absorption onto clay minerals. So this is the reason why shales are so effective. Shales are rocks made up of clay minerals. There's lots of absorption capacity in them, and they take up ionic species in proportion to their concentration in the water mass or in the pore waters, and thus record the ambient salinity conditions. Sulfur, as I indicated before, is a little more complicated because sulfate has to be reduced to sulfide and then preserved, react with iron to produce pyrite or something in order to preserve it in the sedimentary record. And so there's some caveats in its use. Next slide. Let's just take a look at the example of the boron-gallium proxy, and I'm going to focus on this one. Here you're looking at data from modern aqueous systems at the top. Salinity is plotted on the x-axis and aqueous boron concentration on the y-axis. You can see there's a very strong correlation between the two. The R value is 0.99, indicating that boron concentration is an excellent reflection of salinity conditions. The lower plot shows boron concentration in modern sediments as a function of salinity. The overall relationship is not as strong. Obviously, there is a certain amount of noise in transferring the aqueous signal to the sediment. The R value to this relationship is 0.66. Nonetheless, there is a clear indication that boron concentrations are low in the freshwater facies, intermediate in the brackish facies, and high in the marine facies. And so this is the basis ultimately for reconstructing paleosalinities using boron concentration data. Next slide. Brief comment on the use of gallium as a normalizer in the boron-gallium ratio. All four of these graphs are plots of gallium versus aluminum for 4 different formations. You can see that the correlation between the two is 0.99 mostly, indicating that gallium is present overwhelmingly in the detrital fraction and is thus a suitable normalizer for boron concentration data. I've been asked why one doesn't use boron-aluminum ratio instead. That's possible. It would yield the same patterns, although with different values from the boron-gallium ratio. The choice of either gallium or aluminum as a normalizer is essentially rather arbitrary. But boron-gallium is established in the literature and is effective, and so is the proxy that we've mostly used in pursuing paleosalinity studies. Next slide. Here is a plot of boron versus gallium concentrations for modern sediments, and they're categorized based on their salinities as marine, which is shown in red, brackish, shown in blue, and freshwater, shown in green. And you can see that there is a fairly clean separation between those. In fact, 88% of the data points plot in the correct salinity field based on the salinity facies threshold shown here. And the salinity facies thresholds that yielded the strongest correlation to salinity conditions are the two boundaries shown here. The boundary between freshwater and brackish conditions at a boron-gallium ratio of 3, and the boundary between freshwater and brackish and marine conditions at a boron-gallium ratio of 6. And using those two thresholds, 88% of these data plot in the correct field, indicating that overall, the boron-gallium ratio is a pretty robust proxy for water mass salinity conditions. Next slide. Okay, so Eric asked me to address the issue of instrumental needs for this kind of work. The elemental concentration data are generated using the two instruments shown here, a quadrupole ICP-MS, which generates boron, gallium, strontium, and barium concentrations. The latter two can also be generated by X-ray fluorescence, although boron and gallium are not obtained by that method. So ICP-MS is more efficient in order to get the boron and gallium data. Carbon and sulfur concentrations are generated using an elemental analyzer, such as the one seen on the right here. One important point to note is that getting accurate boron concentration data requires analysis of a separate aliquot of the sample and special pretreatment of the sample aliquot to avoid loss of boron to volatilization. Next slide. And this was investigated in a recent study published by Wei Wei in Chemical Geology just this year. He investigated 4 pretreatment protocols for boron concentration analysis. The conventional acid method, which is the one that's most widely used, is to dissolve the sample in a combination of hydrofluoric and nitric acids. But that has the unfortunate effect of generating a volatile boron compound, part of which is lost during the evaporation stage. And as you can see here, the recoveries are only about 67% on average, meaning that there is very substantial boron loss using this kind of standard acid method of dissolving samples. So this is the reason why analysis of a separate aliquot of sample is needed for boron. It needs to be treated with a different method in order to prevent boron loss. And of the methods that Wei tested, he found that the alkali fusion method worked best. We can see 98% recovery on average, indicating essentially quantitative recovery of boron. The other methods he tested yielded better results than the conventional acid method, but less than fully quantitative recovery. So in this paper, which is about to appear in Chemical Geology, we strongly advocate for use of the alkali fusion method for boron concentration analysis. Next slide. So there's Wei. There's the photo of him. He's now a professor at the China University of Geosciences in Wuhan, pursuing his salinity studies. I'd like to take you back to the beginning of our work. The first paper to investigate elemental proxies for salinity was this paper that appeared in International Journal of Coal Geology in 2018. And it's a look at the Paleogene Bohai Bay Basin in northeastern China. Next slide. So here's a map showing the Bohai Bay Basin as it looked back in the Eocene. In the Eocene, it was a large cratonic margin basin that was intermittently separated from or connected to the Pacific Ocean. There was a coastal range that largely separated it from the Pacific and that closed at various periods. But at other periods, there were gaps in the coastal range, allowing marine water incursion into the basin. So the basin had a long history of fluctuation between freshwater lacustrine conditions and near marine conditions. And so we set out to investigate that by analyzing elemental salinity proxies in a long core. Next slide. The unit investigated was from the Middle Eocene. The study interval there is about 300 meters in thickness. We analyzed a lot of different elemental proxies, but found that boron-gallium, strontium, barium, and sulfur TOC worked best. You can see similar trends up section in all three of those. And in fact, the trends reflect a shift from marine conditions in the lower part of the study interval to brackish conditions in the upper part, probably low brackish. So we see a huge shift in salinity. We're recording one stage of isolation of the Bohai Bay Basin, where it was closed off from the ocean and the basin slowly converted from a marine system into a freshwater lake. There were apparently a number of such transitions that were made. We've identified 4. They're shown in the column on the right there, 4 separate stages of marine incursion into the basin, interrupting what was otherwise largely lacustrine sedimentation. Next slide. And just to point out one thing that we overlooked initially, and that is you see a lot of high values of strontium, barium, and selected portions of the study core. Those high values are not meaningful. They represent intervals in which there's a lot of carbonate present and thus a lot of strontium derived from the carbonate, not from seawater directly. And what that means is that these intervals are unsuitable for use of strontium barium as a salinity proxy. So this is something that we didn't understand fully back in 2018, but that we've investigated quite a bit since then. Next slide. So what I'm going to do in the remainder of this presentation is talk about 5 or 6 studies that have made use of these elemental salinity proxies, showing you what can be achieved with these proxies. And I'm going to begin with a study by Jeff Gillido, a professor at George Mason University, who began working in the Appalachian Basin for his postdoctoral work at Arizona State. He's done quite a bit of analysis of various types of proxies and reconstructed water mass structure using them. So let's turn to the next slide. The specific interval for which I'm going to show you data is from the Sunbury Shale. That's an organic-rich black shale of earliest Carboniferous age. You can see it at the top of the lithologic column there. The paleogeographic conditions of the basin are shown in the map in lower right. The Appalachian Basin was an elongate foreland basin with major river inflow from the north or northeast and seawater ingress from the south or southwest, creating conditions in which there should have been a pronounced lateral salinity gradient. One would expect to see lower salinity conditions to the north and higher salinity conditions to the south. So let's take a look at the data. The data published in Jeff's first paper in EPSL in 2021 was based on strontium-barium variation. He subsequently undertook boron-gallium work. The boron-gallium pattern shows the data show the same pattern. So that confirms this work. In this particular case, strontium-barium is a viable salinity proxy. What we see are values that are low to the north or northeast. That's on the right side of the diagram. You're looking at data from 5 different sections, from northeast on the right to southwest on the left, southwest being in the more oceanward direction. The uppermost panel shows the strontium-barium salinity proxy, and the other 3 panels show redox proxies, organic carbon to phosphorus ratio, and enrichment factors for molybdenum and uranium. Notably, all 4 of these proxies show the same general pattern, which is low values to the north, rising to a high value in the second section from the left, the one labeled KEP, K-E-P, and then there is a sharp decrease in values in the section located furthest to the southwest, the one labeled LC at the bottom of the diagram. So overall, the patterns show distinct lateral gradients in both salinity and redox conditions, with, as expected, lower salinity conditions to the north. Redox conditions there are relatively more oxic because there's more input of freshwater runoff from river systems there. We see higher salinities in the deeper central part of the basin, as represented by the KEP core, and more intensely reducing conditions in that area as well. The last section, the LC section, represents, may or may not represent an anomaly. It depends upon its absolute water depth, which is uncertain. If it's shallower than the KEP core, then this may simply be a reflection of vertical variation in salinity and redox properties within the basin. That is, there's a shallowing up onto the Cumberland Sill, which separates the Appalachian Basin from the Rheic Ocean. And one's looking at conditions in a shallower water environment when one gets to that last section labeled LC. In any case, we can see that there are very clear lateral gradients here in salinity and redox conditions. Next slide. And here's the reconstruction of what we think the basin looked like in simplified form. You can see the 5 sections labeled by the circles here. We can outline specific water masses. So the freshwater, low salinity surface layer. We have a water mass that shows ferruginous conditions in the central part of the basin, and one that shows euxinic conditions as you move to the outer part of the basin, presumably recharged by sulfate coming from the ocean, but the sulfate must have been consumed as it moved inward into the interior part of the Appalachian Basin, resulting in ferruginous conditions. And this entire pattern is similar to what's seen in the modern Baltic Sea, and that's the lower panel here, comparing the earliest Mississippian Appalachian Basin with the modern Baltic Sea. So I think it's possible to use these proxies, and salinity proxies play a very big role here, to reconstruct water mass architecture in ancient depositional basins. Next slide. The next study I'd like to talk about is one by Meng Cheng, who's a professor at Chengdu University of Technology in China. This one appeared in Earth Science Reviews in 2021. Next slide. It's a look at the Cryogenian Datong Po formation. The Datong Po is an interglacial deposit that was laid down between the Toarcian and Marinoan ice ages. And it dates to something like 660 to 630 million years ago. It's composed of black shales, but it has prominent manganese carbonate units in it. And the lithologic contrast between the two has long been rather puzzling, but we think we understand it better now as a function of having salinity data. One comment about the paleotectonic setting: these sediments were laid down in grabens in a rift basin, the Nanhua Rift Basin, where there was considerable topographic relief on the seafloor as a function of probably active faulting at that time. Next slide. So this shows the key data from this study. The three columns on the right are salinity proxies: strontium, barium, sulfur, TOC, and boron-gallium. The rest are of the columns show TOC, and then iron speciation data as a redox proxy. Now, let's take a look at the boron-gallium column first on the far right. What you see here is that the black shales yield values that are consistent with brackish conditions and very uniform. So it appears that while the black shale was being deposited, brackish conditions prevailed in the basin. This is supported by the strontium-barium data, which also show essentially brackish conditions. In contrast, if you look at the manganese carbonate units, in particular the three thicker orange bands in the lower part of the section, you see that the boron-gallium ratios are elevated, up around 10, indicating marine conditions rather than brackish conditions. And this is supported by the strontium-barium ratios, which are also high for those manganese carbonate units, although strontium can be associated with carbonate, so that's less diagnostic than the boron-gallium profile. One thing that's interesting is that the sulfur TOC profile shows the opposite relationship. It actually shows lower values for the marine carbonate units, despite our inference that they represent more saline conditions. And this is, I think, due to the unusual dynamics of sulfate, marine sulfate, at this time in the Cryogenian. And I'll explain that in the next slide. There's also a strong relationship between salinity and redox conditions. You'll notice that for the manganese carbonate units, which are more saline, they're associated with ferruginous conditions, as seen in the iron pyrite to iron highly reactive ratio column. And in contrast, the shales are associated with euxinic conditions. Okay, let's go to the next slide. This is the depositional model that Meng Chung developed for these units. The upper panel shows deposition of manganese carbonate, and the lower panel, the deposition, I take that back. I've got that reversed. The upper panel shows deposition of black shale, and the lower panel shows deposition of manganese carbonate. And the key control here is inferred to have been sea level, and thus the amount of exchange of water mass between the open ocean and the basin in which sedimentation was taking place. Sea level was higher in the lower panel when manganese carbonate was being deposited. And higher sea level meant more exchange with the open ocean. And so waters were coming in that were sulfate depleted. And this is the reason for very low sulfur TOC ratios associated with the manganese carbonate. And this is actually supported by a number of other studies that in the Neo-Proterozoic, the global ocean was actually sulfate poor. And sulfate concentrations tended to be higher in coastal water bodies because most of it, the sulfate, was being derived by river runoff. So we see that here as well. Low sulfur concentrations associated with increased marine influence, with higher salinity values, and conversely, in the upper panel, where we have deposition of black shale, that's occurring under brackish conditions, meaning there's relatively greater input of fresh water from continental settings. There's less input of seawater. So brackish conditions prevailed during the black shale deposition, but sulfate was being delivered by river runoff, and that permitted euxinic redox conditions to develop. So here we're seeing paired fluctuations in salinity and redox conditions that are being driven by cyclic variation in sea level elevations, which may in fact be linked to some residual ice someplace driving sea level up and down during this what is putatively an interglacial period. Okay, next slide. The next study I'm going to show you is work by a visiting PhD student from Argentina. That's Mariano Ramirez, who is currently a postdoc at the University of Copenhagen. He published a study in Earth Science Reviews back in 2020, looking at salinity variation in the Toarcian interval of the Cleveland Basin in the United Kingdom. Next slide. Now, this is a very interesting interval of time and interesting in terms of the deposits associated with it. There's widespread deposition of black shale across the Northwest European Sea. This is associated with the Toarcian Oceanic Anoxic event. There have been a couple of hypotheses about why there was such widespread development of anoxia and black shale deposition. One of those hypotheses was published in 2008 by John MacArthur. He proposed that there was an increase in humidity and runoff into these basins that produced a low salinity cap that isolated the deeper water mass, allowing it to go anoxic. Some years later, an alternative hypothesis was published by Thibodeau et al. That paper is from 2018. They proposed that anoxia developed because of sea level rise, that a major transgression resulted in deepening of the water column in these basins, and the deeper water column went anoxic. Both hypotheses are plausible. Okay. Now, there were certain reasons why MacArthur favored the higher humidity model, but nonetheless, I would say that neither hypothesis was proven at that stage. Now, the interesting point about this debate is that the two hypotheses have completely different predictions about changes in salinity variation during the Toarcian Oceanic Anoxic event. The first hypothesis, invoking increased humidity, would mean that water mass salinity must have been reduced in these restricted basins during the TOAE. The other hypothesis, invoking sea level rise, means that salinity in these basins would have either increased if it was initially not marine, or it would have remained constant if it was marine at the outset and sea level rose, it would not have changed significantly. So in other words, these two contrasting hypotheses can be tested using salinity data. And so we saw an opportunity to do this, and we went in 2020 and measured salinity proxies on previously studied samples from the Cleveland Basin. Next slide. Here is the original data published by MacArthur. This is all redox data showing the big spike associated with the Toarcian Oceanic Anoxic event that's colored in light gray. And you can see increases in redox proxies such as the C organic to P ratio, uranium enrichment factor, and a DOP proxy. However, this did not provide any information, direct information about salinity conditions. Mariano analyzed boron in these units and combined that with gallium data and produced the following profile. Next slide. There we go. That's the critical set of data for that same set of samples. And what you'll notice are, first off, that the background values of boron-gallium, that is before and after the TOAE interval, are brackish. You'll notice that the values are between 3 and 6. So the essential salinity condition of this basin was brackish in the early Jurassic. Now, during the TOAE interval, there is a sharp shift to lower boron-gallium ratios, values less than 3, indicating the establishment of freshwater conditions. And this is unambiguous. There's a lot of data there that leaves no doubt about what happened in terms of salinity variation. So this essentially proves the MacArthur model, that there was an increase in humidity that flushed the basin of any salt water, produced a freshwater lake for a short period of time, and then reverted to its normal brackish conditions following the TOAE event. And it essentially disproves the competing hypothesis. Next slide. Mariano has made rather a career out of finding surprising salinity results. He undertook another study while he was at Cincinnati, looking at the Triassic-Jurassic boundary interval in Argentina. The deposits there come from the Neuquen Basin, shown by the star in the lower part of the map. And the rough paleogeography is shown in the inset in the lower right. Next slide. So the Triassic-Jurassic boundary interval, which belongs to the Arroyo Malo Formation, had long been thought to be marine. That inference being based mostly on the presence of what are thought to be marine bivalve fossils. There's an assemblage of bivalves in it, rather sparse and not well preserved, but nonetheless there. And so there are a lot of publications over a long period of time claiming that this is a marine unit. Next slide. Mariano generated elemental salinity proxies for this interval, and all three of them yield clearly freshwater conditions. Boron-gallium ratios are almost uniformly below 3, and the strontium, barium, and sulfur TOC ratios support that. This was a freshwater lake during the Triassic-Jurassic transition. Why are there quote-unquote marine fossils in it? Either the fossils are not marine, or this basin is sufficiently close to the ocean that marine fossil material was carried in occasionally either by storm washover or maybe by biotic agents, birds or animals that carried shells over into the basin. There's some explanation, but the elemental data are unambiguous in showing that this was a freshwater system. Next slide. Just to make sure there was nothing funny going on with these units in the Neuquen Basin, we analyzed 3 additional intervals. So the data I just showed you come from interval A at the bottom of the column on the left. That's the Triassic-Jurassic boundary interval. We then analyzed shales in the middle Jurassic, interval B, and in the lower Cretaceous, intervals C and D, to see what their salinity characteristics were. And very interestingly, interval B showed up as being brackish, and intervals C and D is a mixture of brackish and marine conditions. So it appears, based on this data set, that there was a progressive increase in salinity in the Neuquen Basin from the end of the Triassic into the early Cretaceous, that it became progressively more marine through time, suggesting the development of a better connection with the open ocean. But in the latest Triassic, it was a lacustrine basin. Next slide. The reconstruction of what was happening paleogeographically is shown in this illustration from Mariano's paper. Initially, in the upper panel, you can see that the basin was largely or completely isolated from the open ocean, although potentially by a fairly narrow coastal barrier, and that over time, this barrier became less significant, and there was greater exchange of seawater with the freshwater of the basin, producing over time brackish and ultimately marine conditions. But the transition appears to have been protracted, occurring over a period of tens of millions of years, probably controlled by tectonic considerations in that margin. Next slide. I'd like to present data from a study by Yi Song, who was a PhD student at the China University of Geosciences when she did this work. She came to Cincinnati and visited also, and analyzed a set of samples from the Upper Devonian Chattanooga Shale from a core in Tennessee. And Yi Song is an organic geochemist and biomarker specialist. And what we found was very strong relationships between salinity variation and the algal and microbial communities of this black shale. Next slide. So the interval studied is the Chattanooga Shale. It's of Upper Devonian age, spanning both the Fronian and Fumenian stages. The core in question comes from Western Tennessee. It's called the DuPont 1 core. All of it is black shale. The Chattanooga Shale is a good black shale, organic rich, trace metal rich, and looks pretty much the same from bottom to top, but we found that there is very substantial variation in both its inorganic and organic geochemistry in moving from the Fronian into the Fumenian. Next slide. So here is some of the inorganic geochemical data. The right columns, C organic to P ratio, and uranium and molybdenum enrichment factors, or redox proxies. You can see that all three increase up section. There's a particularly notable increase in moving from the Fronian into the Fumenian part of the section. The three columns on the right represent salinity proxies. And boron-gallium shows in particular a major downward shift from the Fronian to the Fumenian, and the shift is rather abrupt, from marine conditions in the Fronian to brackish conditions in the Fumenian. The strontium-barium profile is a little less convincing, and sulfur TOC shows the opposite pattern. But one point to note about sulfur TOC is it's not effective at distinguishing brackish from marine conditions, and so not reliable in that respect. And so our salinity interpretation is based on the boron-gallium profile. Next slide. Here are the biomarker data for the same set of samples. We have sterane ratios here on the left-hand column, C27 to total steranes and C29 to total steranes. Then we have hopane sterane ratio, HS, and we have aryl isoprenoid ratio on the far right. The sterane ratio profiles are related to the amount of red versus green algal organic matter being input into the section. You can see that red algae dominated in the Fronian, but there was an abrupt shift to green algal dominated conditions in the Fumenian. The shift occurs very distinctly across the Fronian-Fumenian boundary. We also, at the same time, see a decrease in bacterially sourced organic matter, as reflected in the hopane sterane profile. And we see a shift in the amount of input from photic zone euxinic related organisms in the AIR column. So all of these are reflecting major changes in the microbial and algal communities that are tied into salinity change. Remember that there was a sharp change, a sharp shift from marine to brackish conditions in going from the Fronian to the Fumenian. That salinity change appears to have precipitated major changes in the algal and microbial communities. So a very close relationship between these. Now, my opinion is that we're likely to find similar relationships widely in the geological record, but that insufficient attention has been given to both salinity variation and to variation in microbial communities. That is, there's been insufficient biomarker studies of many units, but that these kinds of studies would be very profitable. Next slide. Here's the interpretation of changes in salinity conditions from the Fronian to the Fumenian. Essentially what happened is we think there was a big increase in humidity and freshwater runoff into the basin that resulted in a large expansion of the low salinity surface layer, which we're capturing at the DuPont core because it's located on the upper part of the Cumberland Sill, which is the tectonic sill that divided the Illinois Basin from the Rheic Ocean, which would be on the left in this diagram. So that led to a very significant shift toward lower salinity conditions in the DuPont core. Why do we think there was no comparable shift in the Deep Basin? Because we have data at a number of locations shown by the yellow stars that do show only a minor shift toward lower salinity conditions in the Fumenian. These data are as yet unpublished, but will support this model when we get around to publishing those data. Next slide. Okay, and then the final final study that I'd like to share is one by Jianhong Liu, another professor at China University of Geosciences. We undertook a survey of a number of Neoproterozoic and Mesoproterozoic units to see whether these salinity proxies were applicable to such deep time formations. And the data are summarized right here. You can see that boron-gallium ratios are mostly, well, they range from a low of 3 to a high of 9. In other words, over the range of brackish to marine values. So we're seeing essentially the same range that we see in modern epicratonic seas, suggesting that, in fact, boron-gallium is a robust proxy that preserves salinity information even in units as old as the Mesoproterozoic. The strontium-barium values came back rather lower than expected, with one exception seen right there. But mostly, and that's the one that's associated with the manganese carbonates, and therefore there's probably excess carbonate-related strontium in that one. But the other values are mostly below 0.3, which would be consistent with low brackish to freshwater conditions. We don't think that that's accurate based on the boron-gallium data. Rather, we think that seawater composition has changed over time and that Neoproterozoic seawater had significantly lower strontium concentrations than younger seawater, as a consequence of which one would have to adjust the salinity facies thresholds for the strontium-barium proxy. But in any case, we do see a general pattern between the two proxies supporting our interpretations of salinity facies shown in the right-hand column here. Next slide. I'm going to briefly show you data from two of these units, the first being the Arayanga and Arauca formations, which are from the Amadeus Basin of Central Australia, dating back to about 650 million years ago. All of the values, and you're looking at values for all three salinity proxies on the right here. The red column is boron-gallium, the green strontium-barium, and the purple is sulfur TOC. All of them fall in the marine range, supporting an interpretation of marine salinity conditions, suggesting that they are robust salinity proxies for this particular formation. Next slide. And the second example is from the Barney Creek Formation, which is located in the MacArthur Basin of Northern Australia, dating back actually to the late Paleoproterozoic, 1600 million years ago. Here too, all of the proxies show values consistent with marine salinity conditions, the boron-gallium and strontium-barium values in particular. And sulfur TOC is a little low, but that may be because sulfate was in low concentration in seawater of that age. And I think that would be a ready explanation for why the sulfur TOC ratios are a shade lower than the other ones. In any case, the data support an interpretation of marine conditions in this basin as well. And in fact, that's what we see in most of the Neoproterozoic and Mesoproterozoic units that we examined. Next slide. So that brings me to my conclusion, and I will emphasize just a few key points here. The paleosalinity of bulk shale and mudstone formations can be evaluated using the salinity proxies that I presented today. These proxies show meaningful patterns in many ancient shale formations that can be interpreted in terms of salinity variation. Moreover, the salinity proxy data are commonly correlated strongly with proxies for other water mass parameters. I showed you a number of examples where salinity and redox correlate strongly, or where salinity correlates with biocommunity composition. So this is an indication that salinity was probably an important control in these water mass parameters and needs to be examined in paleoenvironmental studies. And then finally, we found some surprises where salinity proxy data were at odds with long accepted but poorly documented inferences concerning the salinity conditions of certain ancient formations. This is an indication that the salinity proxy data, which are quantitative and generally robust, may correct errors that have been made in salinity interpretations based on other proxies that are less robust. I'd like to thank you for your attention. That concludes my presentation. I'd be happy to stay online for another 20 minutes or so and answer any questions that you have.